Good morning. Welcome to 134, which has three names: Nano 134, Seng 134, and Chemistry 134. This is a really full flight, so if you want to get a credit toward a future flight, or if your travel plans have some flexibility, let me know. We can give you a $500 credit. Just kidding. I see like 1, 2 empty seats, something like that. I don't know what we can do about that, but that's good. There's a lot of interest in polymeric materials, or intro to polymer engineering, whatever you want to call this class is fine. The reason that it has the name Polymeric Materials is that there has been a proposed degree program in material science in our department for a couple of years, and this is one of the courses that was kind of designed in order to go into the materials engineering program, which does not yet exist. So right now it's a just really freaking gigantic elective class, which is fantastic. Okay, so just out of curiosity, how many people are nano? How about chemical engineering? How about chemistry? How about bioengineering? Mechanical engineering? Electrical engineering? Biology? One. Okay, cool. Anything else I missed? Okay, great. Philosophy of polymers? Okay, in the interest of being green, like Kermit the Frog, I am not passing out the syllabus in paper form, so I have it projected here with some of the unknown areas highlighted. So this is the name of the class, which you already know, and I put the name of the lecture hall here because you need to know where it is, but you're already here, so that's useless. But professors put it on anyway, so that's why it's there. Sometimes the reason that anything is done is because it's always been that way, and no one ever questions why that is. But anyway, okay, that's me. I'm Darren Lipomi. That's my office and phone. Don't use the phone number, use the email. But, just, okay. You know that. Nobody uses the phone anymore, right? The office hour, this is the tentative office hour. How many people can't make Friday 3 to 4? Sure you can't make it? You have a class Friday 3 to 4? Okay.
We're assuming we know our schedule.
Okay. All right. Well, because I didn't get a big pushback on Friday 3 to 4, that's where I'm going to keep it for now. If it turns out that there are a million class conflicts and half of you can't show up Friday 3 to 4, we will change it. I'm in the process of reserving a smaller classroom for the office hour, and so we can accommodate as many, up to like 25 people or so. We have 2 TAs for the course, Sam Root and Mickey Finn. Mickey is in the back operating the camera. Mickey took the course 2 years ago. Sam TA'd the course last year, so we have a lot of experience in the teaching staff this year. So their office hours are not known yet, but we'll make them 2 different times during the week that are not Friday 3 to 4, but probably on a Tuesday or Thursday afternoon or early evening-ish, and then another one at a different time. So we'll try to shotgun the office hours so that it's always possible for somebody to come at some point. The textbook is Hemans and Lodge Polymer Chemistry 2nd edition. So this book, this is the best book on polymer science for this level of course. That being said, there is way too much detail in the book than we need. Probably we're only going to cover about 15 to 20% of what is in the book, maybe 25% of what's in the book. But the explanations in the book are deadly accurate and easy to learn from if you spend the time. The authors don't skip any steps in the derivations, and sometimes the notation will be a little bit different from the notation I use in class. I'm sorry about that, but I find this book to be really valuable, especially if you go on in pretty much any field where you will be using polymeric materials, which is, I'm gonna say that 2/3 of you in your careers will be using polymers in some form or another. This is a great book to have on your shelf. I put the book on reserve. I didn't get a confirmation yet. It should be there soon. The supplemental text, Cowie and Origi, Polymers, Chemistry and Physics of Modern Materials. This is almost like a Cliff Notes book to a polymer science class. In fact, the order in which the material is presented is a little bit better than it is in the Lodge book, but they skip a lot of steps, and some parts may confuse you. So it's just a supplement if you want another place to look. This class will have a ton of electronic resources available. So Triton TED is already up. Please let me know by next class if you don't have access to it yet. It just opened up today to the whole class, and we've had some problems with cross-listed courses before, and especially now because we're cross-listing across divisions as well, which makes people's heads explode in IT departments. The class will be podcasted, so we'll have the podcasts available. This podcast will be available. Don't look at what's on my desktop, please. Okay, so the class will be podcasted. The lecture notes will be available. The lecture notes for the entire class are already online, so you can print those out if you want. You can read them on your iPad, but don't check the Facebooks and the Twitters while you're doing that. And you can annotate, so you can just sit back and relax and enjoy the fine content provided by me 3 times a week. We are also recording the classes on YouTube. I won't guarantee that they will always be up or always be up on the day or even within 2 days of class. But I will do my best to put them up as soon as possible. Last quarter, how many of you took Nano 101 with me? Okay, so I think you'll agree that they were posted pretty quickly in general. But I can't guarantee that it's always gonna work. Like, what if the camera malfunctions or something? Or what if the podcast malfunctions? Podcasts can malfunction. So the point is, come to class. I believe that there is a strong correlation between grade received in the class and the number of classes attended. This is just anecdotal because I don't take attendance, but you should still come to class. This is as full as I will probably, as I'm probably likely to see this room until the exam. But I know because so when people get like A's on the exams and I stalk who they are, because that's what I do with my spare time, and I stalk who they are and I look up just to see who they are and if they've been coming to class, and usually the top performers, I know who they are. Okay, because they show up. Okay, the course will be divided into 3 week units. So it's divided into chemistry, materials, and mechanics. And a lot of students get nervous the first couple weeks of class because I will draw a chemical structure on the board and they won't know what's going on. That's totally normal, and don't freak out if that happens. We're not doing any we don't need to follow where the electrons are going. We don't need to know reaction mechanisms, but we do need to know what the structure of a polymer is. Otherwise, we can't talk about polymers. Yeah.
Does the text that goes along concurrently with the class go into the detail about mechanisms in more detail?
The question is, does the textbook go into the mechanisms in more detail? The answer is yes. So then we go to materials. So this is polymers as molecules. The first approximately 3 weeks. What are the structures of the molecules? Then materials. How do those molecular structures arrange themselves in the solid state to give you materials properties? In fact, if you look all around you, pretty much everything in this room is covered in some kind of polymeric material. If you have glasses, everything you're looking at is through a polymeric material because the glasses are high refractive index polycarbonate. This is polyvinyl chloride. This is cellulose. This is cellulose with some kind of methacrylate lacquer on it. This is probably some, perhaps some latex or polyacrylic paint. Again, polyvinyl chloride. Pretty much everything. Pretty much everything is a polymeric material. Why this class wasn't offered for the last 30 years until 3 years ago, I don't know why, but anyway, everything is a polymer. Then we will talk about the mechanical and thermomechanical properties of the materials. So stress-strain behavior, viscoelasticity, why is tape sticky, why is tape sticky, and so on. Okay. There's no class, Memorial Day, 5/29. That's the date of the final exam. Homework for the quarter is posted or will be posted soon on TED. It's not due for a grade. Yeah.
So for the exam 2, that's supposed to be 5-15?
I'm sure that it is.
Okay. And Friday is 4-21. The 20th is a Thursday.
This is, all right, this is why I didn't post it online or print it out yet. I did this while sitting on the tarmac at SFO for 2 hours last night before arriving at 1 a.m. home. Forgive me. That's the last error that I'll actually make in the course, I promise. Yes. No, I'm not going to edit it now. That would be a waste of your time. Okay, that is the day of the final. Pretty sure that's right. Homework, okay, so the homework is not due for a grade. The reason the homework is not due for a grade is because this is an elective and I trust you to do the homework. The solutions will also be posted to the homework, but we will have 3 exams. So 3 midterms is a lot, but it's because we're not grading the homework, and I want to make sure that you're keeping up with the material. Okay, so exam questions will cover material from the lecture notes and explicitly assign topics or problems in the book and the homework. Sometimes the homework is assigning problems in the book. But if a topic is covered in the book, that is going to be like 75% of the book, which is not covered in class. It's not going to be on the exams. Oh, I gave up the joke already. Don't look at that. All right. Grading. Grading will be done in 2 different ways. There will be a curved score and an absolute score. So in the curved score, what we're going to do is assign 30% A's, 30% B's, 30% C's, 5% D's, and 5% F's. It's pretty unlikely that anyone's going to get an F unless you just don't show up. But the reason for that is because we also have this absolute score. So if everyone in here does awesome and we have only grades in the 90s, I'm not going to give the person who gets 100 an A and the person who gets a 90 an F. So that would be sadistic. And although that's not above me, I'm not going to do it because that would lead to poor CAPE evaluations. So this is the other grading scheme that we're going to use, which is based on an absolute score. If everyone gets a 95, everyone gets an A. Such a thing has never happened, but in principle, it could. So we assign the grades both ways, and then the higher of the two grades is what you get. Below that, you'll find my policy on phone use during class, in that there is no phone use during class. Please, it's only 50 minutes. Just resist the urge. Think of it as a mindfulness exercise. You know, I really want that chocolate, or I really want to check Facebook. But you know what? For the next 35 minutes, I'm not going to do that because I have control over my mind. And below that, we find my policy on crying, and that is to say there is no crying in baseball or here. Okay, any questions about the syllabus besides the actual dates of the exams? Exam 2 already having happened, so the highest anyone in here can get is now a B+. Yep.
Are we covering electronic processes in some polymers at all?
Electronic processes in polymers. We will talk about, perhaps we will cover some photoresist chemistry, and so photoresist is the way that semiconductor devices are manufactured. It's a photosensitive polymer, and we may cover a little bit of semiconducting polymers as kind of like an out there sort of research topic, but that would be sort of in week 10 when we talk about kind of the cutting edge of polymers. Yep. Other questions about the syllabus? Yeah.
You said it's not posted online yet, but it will be soon, or it's already posted online?
The notes are posted online.
Okay.
Anything that's not posted online will be posted this week. What is online is the lecture notes and the exams from last year and the year before. So all the exams from last year and the year before, and the solutions are already posted online, so you can get a sense for what the expectations will be. Okay, any other questions? Cool. All right, so what did I bring here? A box full of trash, literally. One of the most important things about this class will be, what I hope that you get out of this is looking at having a property in mind. I need high strength and toughness in some particular engineering application, or I need some polymer to dissolve so it can release some drug delivery nanoparticle, or I need some polymer to be a certain color, or to transport charge, or dissipate heat, or melt, or undergo some kind of reversible thermal transition. So I need to design a material with a particular property, and how do I know what molecular structure to design and what processing techniques I need in order to achieve that that property or that set of properties. So what I'm going to do today and Wednesday is talk about some characteristics of some polymers that we will encounter in our day-to-day lives and what it is about them. We're going to draw some molecular structures. This will be the greatest number of structures that we draw. So a few people will get scared and drop the course, but please don't. You're not responsible for drawing these structures on the exams. And the chemists in the audience are like, no, sorry. But there will be other times when the roles are reversed. Trust me, which is fine. Sadism and all that stuff. So yes. So, and on the other side of the coin, if you see the molecular structure of a molecule or the solid state packing structure of a molecule, then, or in like a solid object or in a thin film, then we know how it's likely to behave thermomechanically and what types of applications that material is likely to be useful for. Polymer science is different from other classes that you might have taken. So some classes in the physical sciences and engineering and math are kind of like you learn some equations and some physical principles, and then when you see the question on the exam, you write down F equals MA or whatever it is, something more complicated than that, and you shove in something you know about the system into F and into M and into A, and then it works out and you get the answer, or you don't, but at least you get partial credit. This class is a little bit different because this will be like learning a new language. So I don't want to use the M word, which is memorization, which for some reason has a bad rap. But let's just use the F word for facts, and that facts are important. So in a job, if you don't know the structure of polyethylene and you're a polymer engineer, then you're not a very good polymer engineer. Structure of polyethylene, by the way, is that's as hard as we're going to. Okay, maybe polystyrene, but that's only slightly harder. So as a result, you'll have to be patient with the terminology that we're going to be using, and as pretty much any scientific field is like 75% jargon, and then the rest is conceptual. Once you know what the words actually mean, then you can pretty much understand the field. For polymer science, let's say that 82% is jargon, as opposed to just 75%. All right. I don't want to talk about that yet. All right. Chemistry, nanoengineering, chemical engineering, bioengineering, these are safety glasses. These are polycarbonate, most likely. It's a hard plastic. Would you believe that this was made from an endocrine disruptor and a chemical warfare agent in a single step? It was. Yep.
What's an endocrine disruptor?
An endocrine disruptor is a small molecule that disrupts your endocrine system. So the glands in your thyroid and your adrenal glands and your hypothalamus and that stuff that I forgot about from 10th grade biology. Yep.
Which chemical weapon?
Oh, I'm getting there. Let me make it to the board, and then all of the mysteries will be solved. So polycarbonate. Poly for many, carbonate for carbonate. Endocrine disruptor sounds like a science fiction warfare agent. This is bisphenol A. Or BPA. Has anybody seen BPA show up somewhere, perhaps at the grocery store in cans of stuff? And yeah, so bisphenol A is toxic, and it's a principal component of polycarbonate and also epoxy resins. And what it does is it interferes. Well, in whatever mechanism it interferes with the endocrine system. Another place that you'll find it is also in cash register receipts. So the thermal paper, anytime you have a thermal paper that's not printed, it's actually just heated up in certain areas to turn those areas black. If you scratch with your fingernail, you ever see how those things turn black where you scratch your fingernail? Kind of like an airline ticket as well are like this. The cash register receipts are like a few percent by weight bisphenol A, so don't go like rolling them between your hands, and because it'll go through your skin. Anyway, it's not very nice. Not very nice stuff. Don't roll them up for any other purposes either. It's okay that that's on YouTube, right? It's okay, I'm tenured now. This is phosgene. These are chlorines. Is that okay? Sorry, I draw a cursive chlorine. I've done it my whole life. It's a problem. This is phosgene. This will react with pretty much anything. So that will undergo carbonyl substitution reactions. Don't worry about that. But these chlorines like to leave, and this carbon atom is reactive. Uh-oh, carbon atom. There's nothing here. Okay, I'm going to tell you, this is not organic chemistry. This is organic structure. Or let's say it's structure of matter that happens to be made of carbon and hydrogen atoms, because I don't want to use the O word, because then people get scared and they say, we're learning O-chem, and that wasn't a prereq. It's not chemistry unless bonds are moving around. This is just the way this is. So let's take the structure of, I'll tell you everything you need to know about organic, well, no. The structure of matter with carbon and hydrogen atoms using just one structure. So this is benzene, which is apparently what you're not supposed to clean your Nintendo games with. I can actually tell how much lamer my jokes are getting as the years progress. Okay, any vertex in a structure of matter using carbon and hydrogen atoms, any vertex is a carbon atom, and the carbon atom has to be bonded to 4 other things. If those 4 other things are not drawn explicitly, then you assume that they're hydrogen atoms. So this is benzene. This is an equivalent structure for benzene. The ends of chains are also carbon atoms. So the vertices and the ends of chains are all carbon atoms. Is that okay? nitrogen and sulfur and oxygen, we will write those atoms explicitly. So it's kind of ironic, right, that organic chemistry, organic structures are the structures of carbon and hydrogen, but ironically, we don't write either carbon or hydrogen. So phosgene is a chemical warfare agent. And bisphenol A is an endocrine disruptor. Both toxic. This one much more so. So this is interesting, right? You take two toxic things, you get eyeglasses. It's a little bit like taking sodium metal and chlorine, elemental chlorine, which are both toxic, and you mix them together and you get salt. I bet nobody thought that was profound. And when you mix these things together, you get something that looks like this. You do not need to memorize the structure, but I'm going to draw it just because. Okay, so this is the structure of polycarbonate. What we do when we draw a polymer is we draw this, we draw one unit, we put parentheses around it, and then we put an N. And the N means how many of these structures there are that repeat. This is called the carbonate linkage. And what did we do when we did this, this reaction? This is called a polycondensation. And what we end up with is two condensation products, two small molecules that were condensed from linking these two things together like Legos. What we're going to find is that we can often make polymers from something that has a C double bond O with a C. So this is called an acid chloride or an acyl chloride that will bond to things like OH and NH2 in order to make bonds. So this is a polycondensation reaction. Polycarbonate is good for optical applications like applications we can abbreviate as apps in 2017, right? Optical apps. So like eyeglasses. And then I'll write down something that nobody uses anymore. Eyeglasses and CDs and DVDs. Okay, so this is polycarbonate. What's special about this unit? Well, the bisphenol A unit is good at providing structural rigidity. So this group and this group, this is a CH3 group and a CH3 group, remember, because it's the end of a chain, and it prevents rotation. So these materials tend to be hard plastic. Yeah.
The phenol groups add bulk to it, so you don't have to do as many residues, or those just kind of conveniently.
They also add bulk. So those benzene rings add bulk and they provide an energetic barrier to rotation. And we're going to talk about concepts like dihedral energies and why some groups allow more bending around them than others, and why that gives you a stiffer or a more ductile material ultimately. Another structure that has kind of a hideously complicated structure, so you don't even have to write it down if you don't want, is epoxy. But I'm going to write it because it's so important industrially, and in in your house when you're trying to fix something and you have the two-part epoxy and you mix it up and you smear it on stuff. What's actually happening? Well, it's also a polymer based on bisphenol A resin. Also, it's in the news because they line the interiors of cans with it, and the stuff leaches out and is potentially toxic. But people have been eating the stuff for decades. So how bad is it? I don't know. Okay, so we have lots of these bisphenol A units. Okay, but don't worry about it. This is called an epoxy group. And what happens when or an epoxide group. And what happens is that so one of the tubes in the 5-minute epoxy, you ever know what I'm talking about, right? Like the two tubes of stuff. So one of the tubes is this stuff, and the other tube is triethylene tetramine. Tetramine, I'm going to say that it doesn't have 2 A's in a row in it. Triethylene tetramine, or TETA. The baker's boy from Hunger Games. Oh, sorry, that's PETA. Okay. Structures will get simpler now. I know some people are saying, "Oh my God, I have no idea what that structure means. I have no idea what any of these structures mean." Don't worry about it. If you're worried about too many chemical structures in the class, we're only going to do it for a couple days. And if you look at the exams that that we had last year and the year before, you're going to find that there's nowhere is anything written, draw the structure of bisphenol A or some epoxy resin. I'm just showing. I'm just showing you because it's important, but not for the exams. So before you drop the class, just open up the files on the previous exams and see if those are the kinds of things that you want to get out of the course. Yep.
What's a resin?
A resin is just a thermosetting plastic that. So I'm using a lot of words here. I'll talk about them more in detail. Thermoset is a polymer that polymerizes or cross-links under heat. A thermoplastic is one that you melt from a solid material and then form into another solid material by molding. So thermoset involves a chemical reaction. Thermoplastic just involves melting and re-solidification. Okay, the most famous polymer that we're going to talk about in this course is also the structurally the simplest, and that's polyethylene. Oh yeah, I forgot I had this box of trash, which is props. Yeah, this is epoxy. This is a piece of epoxy that I cured myself. such an accomplished scientist. I cured this piece of epoxy myself against the polished surface of a silicon wafer. So believe it or not, so epoxy takes on the nanoscale features of whatever it's cured in contact with, which is why it's such a good adhesive, because it gets into the nooks and crannies and forms really strong van der Waals bonds, and even forms covalent bonds with structures if they're activated, if they have reactive groups. And it's very rigid, and it's cross-linked everywhere with the triethylene tetramine, which I've since erased. I'm sorry about that. But it's cross-linked everywhere. So this is a completely percolated network of molecules where you could draw lines from one chemical bond from one corner all the way to the other. And I don't know, there are like 10 chemical bonds in the diagram. No, just kidding, they're more like a mole of them. But anyway, you draw a line from one end to the other, and you can get there without coming across any broken percolative pathways. So this is actually a single molecule. There may be some unpolymerized bits in there, but they're encased in the matrix. That's be a good name for a band. And this is now pretty much a single molecule. So, or the bulk structure is a single molecule, and you can do I don't know, single molecule studies of this or whatever. Okay, polyethylene. Polymers are named after the monomer, regardless of the way in which you polymerized them. So this is ethylene. And what you do is you take one of the, so just as by way of reviewing what we just said about chain ends and carbon atoms, ethylene is this. It's okay if I just write it like this, like a slanty equal sign. And when you polymerize it, you take one of these bonds and you move it to the next one. And then you take one of those and you move it to the next and to the next and to the next. And then you get this. So low molecular, and this is a very useful material, polyethylene for low molecular weight is called paraffin wax. It's what candles are made out of. In fact, if you look at the final exam from 2 years ago, I gave each of the students, and Mickey took this exam, so he'll remember. I gave the students each a piece of parafilm, and I asked, and the whole question was a concept exam, like a concept album, like Sgt. Pepper's Lonely Hearts Club Band, and I asked them to do their own mechanical testing and estimate the modulus and talk about the explanations for why parafilm is stretchy. And you'll learn all of these things in only 10 weeks. So paraffin wax, parafilm, candles, unless they're beeswax candles, which would also be similar chemically to paraffin. Candles, parafilm. Then, and this is N equals, say, 20 to 40. So once the material becomes solid, but not too rigid. So this is N, so 20 to 40 of these repeat units. Then once we get into the higher molecular weight regime, we have something called low density polyethylene, which you will see on the recycling triangles on various products, LDPE. How many of you have seen that before? Low density polyethylene, which has 2% of something called branching in the structure. What's a branch? A branch is something where you have a branch, as in a tree. What do branches do? Branches prevent close packing of the molecules in a solid state. So if you prevent close packing, you reduce the van der Waals attraction between adjacent molecules, and you make it more easy to deform and to stretch and to flex and to work into other shapes. So an example of something that is low density polyethylene is a shopping bag. At least the Rite Aid ones. I don't know about the Vons ones. Actually, don't use these at all. They're bad for the environment. But anyway, low density polyethylene is stretchy. It has some elasticity, but it yields very quickly because it's not very high molecular weight. This is a somewhat more quality type of, it's a higher molecular weight, higher density type of polyethylene. And you can have linear low density polyethylene, which derives its deformability not from branching, but rather from the fact that it has low molecular weight and a high fraction of chain ends in the bulk structure. And this would be, so no branches, but low molecular weight and therefore high density of chain ends, which increase the free volume. Now, what did I say? What does that mean? Branches and chain ends are literally just the ends of the chain, increase the free volume because if you have, imagine logs that are stacked, and you have some logs that are shorter than others, or you have just a lot of short logs. You'll have a very high density of chain ends which prevent close packing of the logs. You'll allow the logs to be, the collection of logs can be deformed more easily because there's more space for an adjacent log to move into. It also tends to lower the melting temperature in a polymer system and also lower the glass transition temperature in a polymer system. And we'll talk more about these concepts as the course goes on. Thank you very much for your attention, and I'll see you on Wednesday.